Okay, great.
Well, that's not good.
There we go. We just have to put the Q in there. All right. So what we're saying is contribute. We're doing one for August 11th through 12th, another one through for December 12th through 13th. And this is for the Perseids and the Geminids. And we're telling people to operate on 6 and 10 meters. And we're having two-way transmit receive stations and monitor receive only. And we're sending reception reports to PSK reporter. And there's a competition, and the rules of the competition are essentially not just the for the rules and guidelines. It's basically setting up that's the experimental design. Okay, so we're telling people to operate in MSK 144. And we're saying a typical Meteor Scatter station consists of a modern HF transceiver, so you can use an ICOM 7300, FT991, or other typical ham radio transceiver, run WSJTX, and a sound card interface. We're saying antennas can be as simple as an attic dipole or a Yagi hex beam quad or Moxon if you have one. Typically, transmitting stations running at 100 watts or more. Does all this sound good to you so far, Rob?
Absolutely, yeah.
Great. MS activity is not limited to the major shower events. Review the materials and suggested websites below and get on the air, typically in the early morning hours starting just before sunrise through an hour or two after sunrise. As soon as the sun rises, other propagation modes such as E-skip, F2 often dominate the bands. Activity will be found on 50.260 and 28.145 megahertz using MSK 144. Saturday mornings are often the busiest times outside of the major meteor shower events. All right, so we tell people to run WSJTX, and that's all running. And then we tell people to do PSK reporter spotting, and that sends all to pskreporter.info. And then that's probably where we're going to get the majority of our data. Let's see. So other WSJT settings unique to the MSK 144 mode. We're not doing a special operating activity, MSK 144 mode. Decode, we say to use deep. We say if you're CQing to the west, leave it unchecked, and if you're CQing to the east, leave it checked. The transmit F tall 200 if your CPU can handle it. RX hertz is 1500 hertz. Report will be filled in automatically when you call someone. Transmit receive seconds is 15. SH marked or unmarked is going to be unmarked, and auto sequence marked or unmarked is the user preference. Does that all sound reasonable to you?
It does, yep.
Okay, yep. Great. Audio recordings of decoded pings. Ham says all about research. Good research requires good data. The more the better. In addition to collecting QSO data from ADIF files and downloads from the PSK reporter, Hamsai would like you to collect wave files of the decoded pings. It's very easy to save wave files when you are running WSJTX. Simply pull down the save menu from the top of the screen, choose save decoded. Wave files will now be stored in your local hard drive. You can use them, find them by doing file open log directory. The menu path, the MSQP rules, and the operating guidelines will explain how, after the meteor scatter events, you can transfer the files from your computer to a secure storage area for later use by the researchers. So we're saving wave files. Operating hints and additional resources from experienced meteor scatter operators. Visit MS-oriented websites such as K5ND. Check out the virgo.exe application for meteor sky view visualization. I will have to check that out. Join our Hamsai group and telecons and our YouTube channel. Listen and see if you can decode scatter MSK 144 pings. Okay, Gary, is this correct? We have 2 meters here.
Yeah, I must have copied that from one of the guys that sent it to me. It was just, the thought was just ahead of time, people can listen there because there's more activity, but I might confuse them.
Yeah, that confused me because if we're doing 10 meters and 6 meters, now we have a 6 meter and a 2 meter. So maybe we can say that might be easy to fix right now really quickly. So we're doing
28.145, I think, is the other one.
and 28.1. Yes. 50. Well, I might do 2. That way, that's right up at the top there. And then okay. Listen on. Note even. Or how about if I do this? Even though we are not using 2 meter for the MSQP, you can also find meteor scatter activity on Does that make sense?
Yeah, it sure does.
Yep.
Okay. And then what's this note even?
Yeah, we can probably take that parenthetical statement out of there because it duplicates what the software set up above.
Okay. So that removes some confusing text there. On your transceiver, set your USB data filters as well as they go. A good time to listen is around 7 a.m. to 9 a.m. local time. The upper MSK window is a 15-second time slot. The bottom MSK. So these are all just like operating hints and tips.
Right.
This text looks like it might be able to be edited for clarity
And
for
Bert.
the page. Yeah, but okay. So yeah, there's a whole bunch of tips and hints I think could probably be edited and wordsmithed. But I think that's not so important. So right now on the web page, Rob, we do not have any specific science questions listed, but you can see what we have written for rules. Do we have actually we include the
On the poster, we were
Okay,
trying to
yeah.
propose some of the science questions, broader ones.
Yes. Okay. Here. So there's another page here that's not quite that you have to dig into a little bit. If you hit the enter the MSQP competition, who makes the most QSOs or generates the most reception reports? And so that links to this page. And now we have objectives Generate research-worthy data resulting from 6 and 10 meter meteor scatter operation. The data will likely be used by the research community to answer science questions such as. And then we have 5 questions here. And these are things that, Rob, we just came up with based on brainstorming ourselves and by talking to some of the other meteor scatter ham radio operators. What's the geographical extent of propagation enhancements due to meteor scatter at HF frequencies? Was a typical duration of useful HF meteor scatter reflections? Is there a correlation between propagation enhancement and meteoroid size or meteoroid velocity? And what other factors might influence the strength of HF meteor scatter reflections? And compare astronomical observations with amateur radio observations. And the target communities include seasoned meteor scatter operators, meteor scatter rookies, those who are new to the mode, researchers with an interest in radio wave propagation. So I guess those are the objectives we wrote down before we started talking with you.
Yeah, I think those are good. I think the that frequency dependence of the strength of the ping and the duration of the ping, I think those are very interesting. And there's some physics reasons, and I've got some math on some slides here that shows what that is. But that seemed to me to be the most useful thing you could extract from this. Let me give you a little bit of background on me. I've just recently retired from NASA a couple of years ago, but had been working for almost 30 years. And part of that time, I was the head of the Meteoroid Environment Office, which is an agency level office, I guess it is, funded by Safety and Mission Assurance. I did that for a couple of years and then handed it off to Dr. Bill Cook, who has been doing it since then. He's the guy that normally when you see NASA says such and such about a particular meteor shower, it's Bill who's doing that. So anyway, so I've been involved in the meteor research, and we have done a lot of that optically. There are a lot of cameras. There's a huge network called the Global Meteor Network now of really citizen science, small cameras around the globe that report back to a central server. But we've also done radio meteor research. Mostly with the University of Western Ontario. They have something called the Canadian Meteor Orbit Radar. And I have some stuff in my slides on that too, which actually determines orbits of meteors. I'm not sure we can do that with, the capabilities of amateur radio. That's pretty tough and requires either time of flight observations or really good timing of something called the Fresnel zones, from the meteor echo. But so meteor orbits are of research interest. I don't think we can do that. Meteor fluxes are the other thing, and that's the number of meteors as a function of time and a function of size. That too is really difficult to do, and these purpose-built radars like the Canadians have are best at that. You really need orbital information, you need speeds and all that, and that's hard to extract from radio. I think that frequency dependence is the thing that fortunately the FCC, opened up the rules just, I think, at the beginning of the year or just recently, where you could actually do MSK 144 on 10 meters. You couldn't do that before because of the baud rate limit. And so now they've just got a bandwidth limit, and hey, man, it works, so you can do that. And there's enough separation there in frequency that I think that could be an interesting investigation. I think the wave files are key to this because you really need the duration of the meteor echoes, is what the radar community calls that, but the meteor pings, to weed out the other propagation modes, because that's going to be even worse on 10 meters, where F2 propagation is as you've said, in the on your page there, and sporadic E, and there's even tropo and aircraft scatter, and there's all kinds of other things that will cause a decode in WSJTX that is not necessarily a meteor. So really the short things, the 1 second or 2 second pings are the ones we're interested in. It would be wonderful if somebody jumped into the source code for WSJTX, and it is available, and modified it where it would actually, you could extract that duration data directly rather than having to fool with a whole bunch of wave files later, because you're going to have to write that software anyway to do that. So I'll just throw that out there as a possible objective. I don't know how hard that is, but I know that a lot of people have worked with the WSJT software and have modified it. It's all open source. It's available, and the MSHV, and there's that JT, what is it, JT call or whatever it is. There are a lot of people have monkeyed with the code, so it is feasible. Might even be worth contacting the developers of the code and saying, hey, we'd like you to add this feature. I've seen people do stuff like that on their chat rooms and message boards, but they usually say, well, there's a source code, you go do it, kind of thing. So I'll just throw that out there as a possible thought, because I think kind of getting rid of the contamination of other propagation modes is going to be key here. You really want to know what you're counting are meteors, and the duration is a really good way to do that.
And it also sounds like, I mean, from what you're saying there, I mean, it almost sounds like sending to PSK reporter is probably useless, because you can't really tell from the PSK reporter spots. You can't confirm what's a meteor scatter propagation and what's just some other spot.
Yeah, I think, for the real science here, you're right. You're absolutely right. Now, it is very cool to have all that stuff reported to PSK reporter, and people being able to see their spot showing up and seeing all that. But yeah, I'm not sure how you would use that to be sure that you're counting meteors there, because if you get a big sporadic E opening, you've got you got a lot of spots. I did some of this back in the early 2000s using TV video carriers. We would just tune a receiver to like channel 3. Remember the old analog TV signals had a big carrier in it, their vestigial sideband or something, but there was a big carrier. And I wrote some count software that did this discrimination to make sure you were seeing a meteor. You want to see something that, and again, I have this on some slides, that has an abrupt increase and then drops off kind of exponentially. Or I just said, if it drops off monotonically, I'm going to count it. And that got rid of those other propagation modes. That's still possible. And I wanted to bring this up as another aspect of this. Those signals are out there all the time. Their analog is gone. It's kind of a thing of the past. But there's a pilot tone in the digital TV signals that is not as strong as the old analog carrier, but it's still strong enough to count meteors. I've been doing it for about a year here from our Marshall Spaceflight Center Amateur Radio Club station. You can do this with SDR dongle, simple receivers. You just tune it to that pilot tone, and I've got some software that I wrote in 2000, and it still works. I can't believe it. It's Windows software, with all the updates to the OSs, it still works. And, counts meteors, puts them in a file, and then you can plot them later. And I have some of those plots.
What frequency is that?
It's, I think the one I've been using is 66.308 megahertz, something like that. It's the VHF low band. So it's right above 6 meters. Now, that doesn't give you that frequency dependence unless you do that on more than one channel. And that VHF low goes up to 70 something, or it's right below the FM band, the FM broadcast band. So there's some frequency dependence there. But
one of the reasons I ask too is because we're deploying these personal space weather stations that are operating up to 60 megahertz. And those stations, these receivers have the ability to just suck in IQ data, and they can decode. We can have it run decoders.
Mhm.
So if these out of ham radio band things were in the band of these RX888 Whisper Demon systems that we have, then it would be feasible for us to just add that into our network.
Yeah. The key there is that you can look at channels 2 through 6, I think, are the VHF low, and those are, because they're lower in frequency, you get longer duration, stronger echoes. You could go into the VHF high, which is up above the FM band, and that's possible. But then there's fewer signals there, and they're shorter. But you have to kind of poke around and find which one of those channels works best for you, because of those 2 through 6, only channel 3 works for me here, because the other ones I get a direct carrier that's so strong that it kind of overwhelms the the process. So there's always a carrier there. You want to tune to one of these bands where there's not a carrier until there's a meteor. So that's you got to fiddle with it a little bit, but that's not hard. That you just tune around and see which one works for you. So that's possible. And it's pretty simple. And then you don't have to have anybody transmitting, because those TV stations are on all the time.
Since you did prepare some slides, would you mind sharing?
I'd be
some of them,
delighted.
especially ones that you think would be really relevant?
Yeah, I'd be glad to. Let me see. Trying to get to the right mode there. And then let's see, where's share. This is based on, do you see slides now?
It's starting.
Okay. This is based on a slide deck. I've done a talk. Okay, good. I've done talks. Let me do the read mode here. At Huntsville Ham Fest and various places on this topic. I love this picture because this is I think a Lyrid meteor photographed from space station. Looking down, you can see Florida down there, and Miami area, and Atlanta up here. So anyway, so I think I've already said all this stuff. We like flux as a function of meteoroid size and time. That's tough. The scattered power, and I'll show you the equations for this in a second here, is proportional to the wavelength cubed, and the signal duration is proportional to the wavelength squared. There's pretty strong dependence there. So between 10 and 6, there should be, quite a bit of difference there. And then we got the contamination problem. There's another one here, and I'm only vaguely familiar with this, but I think this is something that we have the opportunity to investigate, is something called the initial trail radius effect. And what this is let me jump to another. I want to show you some of this geometry because that's all real important. Let's see here. The development of a trail, a meteor trail, say the head of the meteor is down here on the lower right. As a meteor comes in, of course, it causes ionization, and there's a bunch of free electrons that come out, and they diffuse. They start spreading out, and so the trail gets bigger later, and that's all really important to ways of determining the speed of the meteor and such. But the faster meteors ablate higher. They're higher in the atmosphere. They burn up higher because they're going faster. And so the atmosphere up at that altitude, ablates them or burns them up. And because that's higher, that diffusion happens quicker. And so the meteor trail is bigger at higher altitudes, which is for faster meteors. So there's some observational bias that comes into this. It has to do with the radio signal bouncing off the near side of the trail and the far side of the trail, and some interference effects. And so that's why you really need multiple frequencies. And that Seymour radar, the Canadian Meteor Orbit Radar, runs at 3 frequencies. And I've got those here somewhere. It's like from 17 megahertz up to 40 megahertz or something like that. And that helps untangle this. I've now told you all I know about the initial trail radius effect, but it is something that's important. And I think as we go along here, I'd be glad to try to set this up, is try to engage somebody from University of Western Ontario. Dr. Peter Brown up there runs that Meteor research group, and they might be glad to come talk about that, talk about the Seymour radar and some of these effects. So if you're interested, I can, touch base with him and see.
Definitely.
Let's see. So all of this stuff, I've got the references down here. This DWR McKinley, if you can find that book online or a used bookstore or something. Yeah, there we go. McKinley. It's like from 1955 or something. So it's as old as I am. That's really an excellent book. It's got all the math in it. Let's see. Let me back up here. I think we've talked about most of this. Yeah, the wave files, receive on the DTV. Yeah, I think we've talked. Okay, there's the Seymour specs right there: 17.45, 29.85, and 38.15 megahertz. They have a pulse repetition frequency of 532 hertz and a pulse width of 75 microseconds. Some of you up in that part of the country should probably hear their signal occasionally, especially during meteors. They have Yagi antennas that are pointed straight up, and so it's a backscatter system. They're listening between the pulses and operating on the three frequencies. So you may just tune to those frequencies. You might hear them. Down here in the southeast now, we're pretty lucky because N4WLO, who lives down near Mobile, Alabama, has beacons that he runs on 6 and 10 meters. And you can see they're slightly different frequencies. It's not in the normal communications frequencies, but it's nearby. And I've been listening to the 28.189, the 10 meter here occasionally, and can hear meteors on that fairly regularly. I haven't done a lot of meteor scatter since the 10 meter capability opened up. I did a couple of showers, I think. There wasn't a lot of activity there. I'm hoping there will be more because I think people will find it works better. So these are some of those digital TV counts. These are plots of the meteor count. There's a 1 hour average, a boxcar average there in blue, and then the 15-minute counts. And these counts come from that software I was talking about. This is on 60.3085 upper sideband. We're using an ICOM 8500 and a dipole, and it's just strung up, kind of out behind our ham station. And you can see that a very strong diurnal variation here. 0 UT is around sunset, roughly locally, and you see how it rises during the day. This is 12 August during the Perseids, and then it drops off, and you get a more strongly peaked diurnal variation up here. And all these Zoom things are in the way. I can't see the date. There it is, 25 June of last year. So this is just some Python code I wrote that reads from the count files. So this is what that digital TV stuff can do for you. It's amazing that it works that well. Let's see here. Some of the geometry, and I think a lot of people who do meteor scatter don't really understand this, but Virgo, the software you mentioned there, kind of handles this in a real simple-minded way. Not every meteor is going to give you a good scattered signal. The meteor trail needs to lie tangent to an ellipsoid that's defined with the transmitter and the receiver at the foci of that ellipsoid. So, draw an ellipse with the transmit station, the receive station at the focus, each focus, and then spin that around. It's kind of a football, rugby ball kind of a thing. And the meteor really needs to lie tangent to that. All this math is in McKinley. And so there's kind of two types of meteors. There's underdense and overdense. The underdense ones are the short ones, and those have to satisfy that condition. The overdense ones, the really strong meteors, they don't have, they might not satisfy that condition, but eventually, as they diffuse, it's kind of like a Coke can crinkling up, and so you can get surfaces that cause reflection, and it is almost a reflection thing for these overdense ones rather than a scattering thing. So really strong meteors don't have to necessarily meet this condition, but the weaker ones do. And of course, the stronger ones last longer, and they're good. But I throw them out in that count software I have, because we couldn't do anything with geometric calibration. But there's only a small number of meteors that meet these conditions, and so you can see meteors visually, and you'll never hear a ping. But boy, sometimes you do see one and hear one at the same time. We did a lot of validation when we first started all this to make sure. So Virgo knows where the radiant of a meteor shower is, and it tells you what direction you should point your antenna to improve your chances of meeting this specular condition. And if you look at this and think about it for just a second, you see this one right here, that's coming from straight overhead. So when the radiant goes directly overhead, which is when you see the most meteors, the specular condition is met along the horizon. So meteors that are coming down and they're up here, you're just not going to get a good reflection off of them, or a good scatter off of them. They're all down near the horizon. So this process kind of goes blind when the radiant is directly overhead. And that's true for the backscatter radars as well. And so calibrating all of that is a huge mess. And so the Canadians have figured that out with their radar system. But that's why I say fluxes are really hard to measure because of these conditions. But it's good for people to know these conditions, because depending on where the shower radiant is, you may be better pointing north-south than east-west. And Virgo tells you that. That's just a little further. There's some of the angles that are defined there in the math, and I threw in that ellipsoid. Okay, so this is the power scattered, and there's transmitter power. There's a gain of the transmitter antenna, the gain of the receive antenna. This is for forward scatter. This is two station. This is not backscatter radar. There's an electron scattering cross section here, an electron line density. That's Q squared. And all these angles are defined in that previous picture, almost all of them. But the key is this lambda cube here. This is a wavelength cube. So the scattered power goes as the cube of the wavelength. That's pretty strong dependence there. So that's one key thing. And there's another equation here. This is the duration of the signal. And you see a lambda squared up there. So that one, the duration of the ping goes as the square of the wavelength. And there's some angles here, and D is the electron diffusion coefficient right there. So obviously how that diffuses is important. And that depends on altitude. And the altitude at which that occurs depends on the speed of the meteor. So there's stuff you could extract here if you have enough data. I've never done it, never tried it, but I know that, the math says you can go get some of this info.
What do the speeds come out to be?
That's a good question. They are typically, I think some of the slowest meteors are down around 10 to 15 kilometers per second. The fastest ones are the Leonid meteors, because those particles are coming almost head on, or hitting us head on from their comet orbit. They came from comets. Those are 72 kilometers per second. So there's a pretty wide range.
Yeah.
And I think I've got a slide here somewhere that has Perseids and Geminids on it. Geminids are a little bit slower. They're 35, and I think the Perseids are 50 something kilometers per second, somewhere around there. But this kind of works out that math there, looking at those things, the relative strength, the lambda cube term, and then the duration. And I just set the 6 meters equal to 1, and you see you got a 5.7 advantage when you go down to 10 meters for the strength, and a factor of 3 for the duration. And then I did the strength in dB here if you wanted that. But you see the disadvantage of 2 meters here. But people usually have more gain, antenna gain on 2 meters, especially if they do satellites or moon bounce. But that's narrower beam and all the problems that go with that. So anyway, that's that frequency dependence, and so I think that's something useful. The echoes have a pattern that looks kind of like this. They go up abruptly and then start dropping off, but here they're just they don't show the diffusion. But these are called Fresnel zone, or they're called by the Fresnel zones here, and you can read about that. Aircraft scatter does similar stuff. You hear that kind of wah 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 wah. When you hear like an FT8 signal that's scattered from an airplane. So a similar thing happens, but it's really fast, too fast for WSJT to keep up with it. So another look at that. We already talked about that. Kind of the cross section here of the ionization trail. There's some of the angles there that showing how the electrons may be distributed and then they diffuse out.
So what is the size of the trail?
That's really interesting.
And large. How much physically is it?
what Peter Brown says is that it's amazing that you can have a little grain of sand sized particle, and it generates an ionization trail with the radar cross section of a battleship. So these can be really big, many meters across, and even kilometers long, and it depends on the diffusion, but yeah, it's really big. So that's why it's hard to think about this, but you would never see one of these particles out in space, only when it comes into the atmosphere and generates all these free electrons in the atmosphere. And it's not so much its material, but it's just the atmosphere that it's heating and ionizing.
Did you ever detect cosmic rays?
I don't know. I've wondered about that, Mary Lou, that there's been some, there are cosmic ray detectors that look for the light flashes for cosmic rays. There are these big fisheye lenses that look for that. I'm guessing they probably generate some kind of ionization trail too, but I don't know. That's a really good question. I don't know about that.
Okay, I used to have some cosmic ray scintillation counters.
Mm-hmm.
They were interesting to look at. They didn't look at the sky. You had them in your hands.
Sure.
We had a set of 4 of them, and you could arrange them in different geometries. Mm-hmm. So you could, if they were beneath each other, you were looking straight up, and if they were offset, you were looking off to the side for only the cosmic rays that had a ping in each of the detectors. So I wonder if they did anything with the sky. I don't know.
Well, they do. I know they make flashes in the sky that are sometimes measured. I would guess that maybe you could get enough ionization there to get some signal off of, but I don't know if anybody's pursued that. I never looked into that.
Yeah, that's the Cherenkov light. It's very faint, but can be determined by wavelength.
Yeah.
Okay, never mind.
No, good question. So the meteoroids, about 90% of them are cometary material and associated with comet orbits, and the meteor showers. Most of them we know exactly which comet those are generated from. There are a few uncertain, but
do we know their chemical composition?
Somewhat. There's a lot of probably volatiles, ice in some of these things down inside the middle of them. The dirty snowball. That's the typical model of a comet.
Right, but I suspect that the ice would be gone, and what you're seeing is the metallic compound.
But certainly if the particle is small enough, if it's a larger particle, there could be ice inside it. But on the outside, it's probably gone. The densities are pretty close to 1. The Geminids are asteroidal, and their densities are close to 3 grams per cubic centimeter.
Cool.
But they're fluffy. You see that picture down at the bottom there, that interplanetary dust. Now that was collected in the stratosphere by like a U-2 plane or something, and so they're kind of fluffy. And then so those are meteoroids. When they're in the sky, they're a meteor, and if you stub your toe on it, it's a meteorite. We always try to get that that nomenclature down.
I wonder if there's any correlation or can be done. So this is looking very ahead, with the sort of things that you might find from this data about the sizes of the meteoroids, and then with the people who collect them on flypaper and such like that, that the ones that hit the ground, or hit the rooftop, that sort of thing. So there are amateurs who collect that sort of stuff, these tiny, tiny little dots of stuff, that actually make it to ground level. Or actually, well, they make it to the upper atmosphere, they slow down, and then they just sort of drift down. They don't actually come to the ground. They come to up here, stop, and then drift down with the wind.
Right. Yeah, and I think there's a good indication that the sporadic E propagation is from metal ions from meteors as well. But yeah, the ones you're talking about haven't fully ablated. Yeah, I think it's the smallest ones that may not ablate, that they can cool quicker radiatively, so that they don't burn up. And I don't know a whole lot about that stuff, but yeah, I've never heard of anybody trying to do those correlations, but I guess it's feasible. It depends on how long it takes for the stuff to fall out too. Just a couple of meteor showers here associated with Comet Halley, just to show this comet correlation. As Halley comes in, when it crosses the Earth's orbit, we get the Orionids in October. Pretty good shower. And then as it leaves the inner solar system, we get the Eta Aquarids. And of course, it's leaving particles along behind it all the time that are roughly in that orbit. So even when Halley's hanging around way out here, it looks like it's at aphelion last year, there's still particles that it left behind. And so we still have Orionids and Eta Aquarids every year.
So I have a question here looking at this diagram. So when the comet comes in and makes the Orionids, it has not passed perihelion yet, so maybe it's not shedding too much fluff. Then it goes past the sun where it gets heated up and the top meter fluffs off, and then as it heads out, so maybe I would think the Eta Aquarids would be stronger than the Orionids. Is that true or not?
Well, I think because these particles are just kind of permanently in this orbit and were left behind many years before, and it could be hundreds of years before, I don't know if there's a strong correlation there. We're getting better at predicting meteor showers, and the Meteoroid Environment Office does this every year for spacecraft safety purposes. The space station crews, before they do an EVA, they look at, is there a shower going on? So, and we will be doing that for the lunar EVAs as well. We've already talked to the programs about that. That's kind of my day job is human landing system now, the lunar landers and the space environment for that. But anyway, this is kind of gives you an idea of how these are associated with comets. And here's some of the showers, and the speeds are over here on the right hand side. So let's see if I got that right. The Eta Aquarids and Orionids are both around 60 something. Those are the ones associated with Halley. Geminids are 36. Those are a little bit slower. And that's from an asteroid named Phaethon that goes in very close to the sun. And that's one of the most reliable showers, I think. And Perseids are 60. So, there's a pretty good speed difference between the two big showers that we're focusing on.
Now,
but as you
ChatGPT is telling me that, so you've got the Eritids, which are happening right now. It says daytime. ChatGPT tells me that if I get up 45 minutes before dawn, I might be able to see something. Is that true?
Yeah, yeah. The radiant is in the daytime sky, so they're mostly in daytime. So that means the reason we know about them is because of radar, not for optical reasons. But yeah, usually there's a chance to see a few of them. I don't know if we ever have done any optical observations of those.
So my wife gets up every morning at 4:30 a.m. to go swimming. Is it
Yeah.
worth having? Is it worth asking her to wake me up too tomorrow morning to go out and look at these things?
What? Why not? Yeah, I said, hey, you can watch the sunrise. Watch the sunrise together, right?
Yeah.
So yeah, yeah. Now that's all shower stuff we've talked about so far. It's really important to understand the sporadics. These are the ones that are there all the time, and they don't vary much over the year. They're kind of isotropic. They're kind of from all over the sky, but not exactly. There actually are sources for the sporadics. And so I like the fact that on your webpage you said, hey, do morning observations, try to make contacts in the mornings. Anyway, because there you're going to get the sporadics. So let me try to explain this plot here, because getting this in your head is really useful. This is the ecliptic, which is the plane of the solar system, is running across the middle. This is, I think, called a mole-wide projection. So it's take the whole sky and smash it out flat. And so the sun is over here. The direction of the Earth's motion is right in the middle where that star is. So that's called the apex direction. So that's where the Earth is headed. And so you have these sources. You have a helion source that's close to the sun, an anti-helion source, and then there's the north and south apex sources. Now, these are observations from Canada, and so they're a little bit biased to the northern hemisphere, but this is pretty symmetric. There's also something called the north toroidal source, and we know from observations, radar observations in the south, there's a south toroidal source. These are associated with different types of meteors. There's Jupiter family, different kinds of comets, Jupiter family comets, Halley type comets. And I don't remember the correlations between these, but that's pretty well understood. When you are looking at the sky at sunrise, the sun is just coming up. This circle here is sort of roughly your field of view. And look at that. All of these sporadic sources are in your sky. That's why in the morning you see more sporadic meteors. It's that simple. It's usually stated as, well, you're on the front bumper of the car or on the windshield of the car, and more bugs are going to hit you as you're going down the road. That's one way to think about it, but the sporadic sources are all visible then. So that's the sunrise sky view. Now at sunset, the part of the sky you're looking at is this left-hand side and the right-hand side, and there are no sporadic sources in there. So you don't see many meteors right around sunset. But as the night goes on, more of these, the anti-helion and eventually the north and south apex sources come into view. So that's really important to keep in mind. We understand why there are more meteors in the morning sky. You've all seen the FT8 ping. I don't know if my audio is set up. Let me try to play this. You hear any audio?
No, you may have to press the share audio button before you share your screen.
Yeah. Let's see.
And you can do it as you're sharing too. There's a way you just click on the options there and you can share your audio.
Let's see. Options. Let's see. Share screen. I've done this before. Oh, maybe it's in the under the audio menu. Audio settings. Well, I don't know how much time we want to waste on this. We're getting near an hour here. I don't know what y'all's time is here, but maybe we'll do this some other time when I've got time to figure it all out. Sorry about that. But you've heard FT8. What the point is, there was a meteor ping on the FT8 decode here. Somebody was working FT8 over here, which I wasn't hearing until there was a meteor. This is on 6 meters. And so there's a little short, very short ping right there.
What did
Just
it sound like?
It kind of a ping. I really should get that working, huh? Okay.
Here, okay.
All right. Walk me through this now, Nathaniel. What do I need to do?
The easiest thing to do is stop sharing your screen for a minute.
Okay.
And I can actually stop it. And then
All
now
right.
press share again. But before you actually press the next button to share, there should be a little checkbox that says share computer audio.
Share sound. Got it right there.
There
Okay.
you go. And then just hit share. Now you should be good.
Okay. All right. Let's see if you can hear this now. Did you hear that really high ping right at the beginning? Let me play it again. Do it again. Right there.
I think I heard it.
Yeah. All right. I've got something. I've got a better one here. This is the difference between these underdense and overdense meteors. And this is, again, listening to video, TV video carriers.
Yeah.
You heard all the little short bloop, 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 and then you hear that, that lasts for a while. That's an overdense one. Most of them are underdense. All right, so that's not what MSK 144 sounds like. That is a grunt. It's a highly modulated, multiple frequency kind of a thing. This is what those digital TV things sound like. So, and I think I've said all the words that are on there. This is what they look like from that Seymour radar. And look at that profile down at the bottom. See, it comes up very quickly, and then you see those Fresnel zones in there, little up and down, up and down. And by measuring those things, you can actually get the speed of the meteor. But I think that we don't have the time resolution with MSK 144 to do that. So that's an underdense echo, and then this is an overdense one. And you see how it's just kind of lasts a long time and it's sort of all over the place as that metal tube crinkles up as the diffusion and the winds, the mesospheric winds upset the trail. All right, so this is what the digital TV looks like. This is just a SDR play, and you can kind of see sort of a faint carrier in there in the waterfall, but there's a meteor here and there's a meteor down there. And so this is really easy. And this is just, I think this was with my 6 meter element on my hex beam here. When you have a more resonant antenna, you get a little bit better signal. Here's the the frequencies up here, channel 3. You see that, they go up to 82 megahertz. So there's some spread there. So that's something to think about. Might want to add that. That's what the digital TV signal looks like. I got this off the internet. There's the pilot tone right there. Most of the power is in this, what looks like noise, but that's that, highly compressed video, digital TV video, but there is a pilot tone there. I think we talked about the speeds. The altitude of ablation is 80 to 120 kilometers, and that's the E layer. That's where sporadic E happens. I think the rest of that's basic stuff that you'll probably know. That's what Virgo looks like, and see, it's telling us that for these sources over here, and it shows the sporadic sources as well. But there's a North Taurids I see, and some others. They're over here on the eastern horizon, and it says, point your antenna north. And so the way it's figuring that is because of that ellipsoid that I was talking about, and the meteors needing to be tangent to that ellipsoid. Yeah, all this is just MSK 144 stuff. But hey, since we got the audio working, why not? Let's play that. You heard just a little kind of sound.
Mhm.
That was this signal, and it decoded, I guess, a couple of times there. Let's see. This is this one. Now that could be that's a different propagation mode. That's probably not a meteor, and so that's probably an airplane or something. I'm not sure what's going on there. But you need to, if we can be sure that we're counting the short ones, then we know they're meteors.
Yeah, someone asked me the other day, how do you know the difference between something that's coming in via meteor scatter and something that is from other propagation? So it's really looking at the duration of the signal.
I think that's the best way to do it. Yeah, it really should have that profile of that abrupt increase and then kind of dropping off exponentially. But if you just say, "Hey, it's a short one," if you know that it's short, a second or two, it's most likely a meteor. You still could get some contamination, but it probably is. And I
So
think
you
that's
get that abrupt decrease. That's why do we have the abrupt decrease right after?
that is a good question. Let's see if I can get back to. Uh-oh. Oh, this audio in here. I'm going to have to stop that and go back to. Oh, I thought that this would show it, but it doesn't really. It's related to this. This is showing it kind of staying constant, but it's that diffusion is part of it. The trail is diffusing, and so the scattering, is reduced. Um, I don't know if I've got a good one that shows that. It's this kind of is showing the underdents, it's up and then down, and yeah, the overdents may last longer over that time scale.
Do people know the actual amount of ionization, the electron density in these
I,
strips?
I think they probably can back that out, that Q squared that was in that equation there. And I don't know what that is, and I'm not sure, what they do with that. But yeah, in principle you could figure that out. And that's related to the size of the meteor and the speed of the meteor. So that's why it's important in this calibration thing to know the speed. During a shower, you pretty well know the speed of most of the meteors. There could still be some sporadics in there, but you can say, hey, that's a Geminid. That was 35 kilometers per second. And then you've got a chance at backing out the size of it. But that calibration of your antenna pattern figures into that, and then that geometry, that specular geometry thing, it's a hot mess. We kind of gave up on it. We tried 20 something years ago to work through that. And we just said, oh, we'll let our Canadian guys with their more sophisticated backscatter radar, let them go work it out. And they did.
Do they have other people who are using backscatter radar to look for these things? How about
There,
the Darns?
yes, there are. There's one in the southern hemisphere. It's called Samer, and I can't remember what country it is. It's pretty far south in South America. And that's actually partially funded by NASA, but it's a similar radar. These radars were actually built for upper atmospheric wind research, and so they were measuring the meteor. The meteors were providing a signal, and they could measure the wind speed in the mesosphere with that. So that's what they were initially built for. Now they've kind of been modified, and the software modified to focus on the meteor physics. But yeah, there's Samer. There was a big one in Australia, and I can't remember what that one was called. It was very high power that operated, I don't know, 30, 40 years ago. So there are some around. I think there's some in Northern Europe. like more radio dish type things, radar. So we use the what's the one on Kwajalein? It's actually a defense radar. It's used for they measure warheads being flung from Vandenberg out to the Pacific, to measure that phenomenology. And we used that during Leonids back in 1998, I think it was. So there are some big radars, but they're mainly VHF radars. That's where this scattering is most effective. So I think that's about all I told you all I know. So give you some things to think about.
Thank you.
Thank you so much, Rob. This has been incredibly interesting and helpful.
Well, good. Glad to hear that.
Well, Deep, do you have any questions?
Yeah, thanks for sharing this. I was listening to your presentation, which you mentioned in the emails, the similar thing, and you were highlighting the ellipsoid thing, the tangent or being it in. So in addition to doing, definitely, I guess, pursuing the lambda dependence or frequency dependence will be very good with 6 meter and 10 meters. Can we also go for this theta part?
I'm sorry, say that again.
Can we also check this theta part of it, the angle dependence of it somehow?
I guess yeah. If you knew with a shower, you would know that geometry. Sporadics are kind of, coming from multiple places, but with a shower, I have to think about that. That's a good question, Kuldeep. I'm not sure. But I think you could, where they are not meeting that specular condition, which is the optimal, is there something, could you extract that? Let's see, where was that equation? Yeah, some of this angle stuff in there, those phis and the phi angles, and there's a beta and omega. Possibly so. I don't know. That's a good question. I think that's a great thing for you to look into.
Yeah, thanks. Thanks for sharing. This has been really interesting and informative.
Good.
So Rob, spaceweather.com every day has a list of sporadics that have been observed somehow. Do you know what they are?
I don't. I haven't been tracking that. I know the guy who does that that site, but I haven't been tracking it lately. It could be. I think he had a link to the Seymour output, but that was, oh man, I've got to think about what that link is. The Meteor Environment Office hosts a site. I think it's Meteoroid. Is it meteors.nasa.gov? Oh gosh, I've got to look that up, and I'll email that to you guys. You may find it before I find it. But it gets you to a page that has some of the Canadian Meteor Orbit Radar output and the data from a Fireball camera network.
Oh, I
that we
think the
have.
ones that he has are fireballs, but
Yeah, I'll bet they are. And what that is we run a few of them here and in New Mexico and Arizona, and you have to have at least two cameras, and you can triangulate between the two cameras. This is all automated, and it sees a meteor in the sky, and it can actually figure out the orbit. And I believe that's what that is. I think I understood that he was getting that data from there. So yeah, that's probably it. And then there's this global meteor network, which is a little slightly more sensitive cameras, more modern cameras. They're not just video; they're modern like webcam type stuff. They're very sensitive, and those are doing similar stuff, and it's just amazing. They've got them all around the world. So a meteor can't sneak by anymore. Somebody's going to see it and record it. its demise.
I think this is really good. I think so. I have a couple thoughts on this, Rob. First of all, I think what you've presented is really something that we at Hamsci are missing in terms of expertise. So this is extremely helpful. Two, I don't think I have your original email with what you wrote about suggested science topics or research questions. So I might suggest, if Kuldeep is up for this, Kuldeep, do you have that original email from Rob? And would you mind taking a crack at revising our MSQP objectives and and iterating on them with Rob and with us? Because I think it'd be nice to highlight that, we're really trying to look for that frequency dependence and trying to understand that a little bit better.
Yes, sure. I am up for it.
Okay.
And
So
I believe I had that email, the first email which Rob sent to the Hamsci, which has the potential science questions. That's the email you are referring to? Okay, yeah, I have that.
Yeah, so why don't you do that? So you can take a first crack at that, and then iterate on it with Rob, and you can include Mary Lou and Gary and I, and that way we can kind of come up with a set of questions that we really believe. And then once we're happy with that, I'd like to revise, revisit the MSQP web pages to make sure that everything that we have on there is consistent with the science objectives, and that the text on the bottom is a little bit better crafted. But let's just focus on getting the science objectives down first, and then we'll be able to circle back to the procedure and those things. The other question I had from interacting with some amateurs, and even it's a question for myself, I talked to another Meteor Scatter guy. His call sign escapes me for the moment, but he hosts the Meteor Scatter Facebook page. And I asked him for recommendations on like what sort of equipment to use, and he immediately said, amplifiers with a few hundred watts and some more substantial antennas. And I said, well, okay, I'm a little budget constrained and time constrained, and many of our participants are. And one of the things that he came back to me and said is that we really don't know what the minimum level of equipment is for operating Meteor Scatter. Would you agree with that statement, Rob?
I think that's true. Now, when I first started doing some Meteor Scatter, it was all 100 watts, on 6 meters. I did better when I went to our Marshall Club station and used a 5-element Yagi with 100 watts than I did with my two-element Moxon antenna that I had built here. So antenna certainly helps, but it's not hard to build, a 6-meter antenna. 10 meters a little bit harder. More power does help. Now I'm using a KPA 500 now, and it's certain, like in all things, it helps. But I think people with 100 watts and a couple of elements, or even as you said on the site there, a dipole, you're going to hear people and you're going to be heard. It's just harder with lower power and lesser antenna.
Would it be a fair research question for the MSQP to be, what is the minimum equipment you can use?
I think that would be good. Yeah, if you can, you know how Whisper carries with it your power level, and so you would have to have people self-report that. Obviously, that's not going to be encoded in the MSK 144 signal. They'd have to self-report what kind of antenna and how much power they're using. But yeah, when you start doing all the big data analysis, that would be interesting, I think.
Because I think that would be a really nice question HAMSA is supposed to both help the science and help the amateurs.
Mhm.
And I think if we can help answer a question of what is a minimum station, or maybe what type of performance can you expect from these different types of stations, maybe that's a nice way to put it.
Yeah.
If you've got this level of station, what type of performance can you expect and how well will it work? Maybe that's a good way to phrase it. I think that might be a nice result that we could get out of the MSQP and put that all into one table.
Yeah, I certainly think so. I think that's a really good idea. And I hope if nothing else comes of this, that it motivates more people to get on 10 meter meteor scatter. Because I think if people start actually doing that, they're going to realize, hey, this is better, or let's see if it's better, but it should be better. The math says it ought to be better. Right. So,
yeah. Okay, so that's good. Gary, do you think, I think, so I'm asking Kuldeep to revise the science questions, but maybe do you think either you or some of the amateurs can work on writing up the part about what station, what's kind of what performance we get from different types of stations, and how would we collect that data?
Yeah, I got you. That makes sense. It is an interesting question.
That would be a really good kind of question for the amateur group to lead. And then maybe, do you think you can also reach out? I think there's some real need, or there's a real opportunity to find someone who's good at looking at the WSJT source code and making some modifications. And I wonder if we can recruit someone from HamSci somewhere, or a few people who are good software people that would be interested in implementing some of those changes that Rob is making.
Once we make a case for doing it, it's free to ask, right? So we ought to ask. If you don't know, if you don't ask, you don't know.
Yeah. Let me write down some of these things. So this is June 11th, 2025, meeting with Rob.
Yeah, I think I'm sure there are people in the ham community. You probably got students who are pretty good programmers who could jump right into that code and figure out how to. All you need to do is figure out how long that ping was, and yeah, it should be pretty straightforward. You could ask, was it K9AN? Has Steve Frank? He's the F and FT8. I think he was involved with MSK 144 too, or K1JT himself. Just say, hey, how hard would this be? Point us in the right direction. Or somebody could just look at the code maybe and figure it out. I think some of that, the deep search stuff is in Fortran, which kind of tickles my fancy because I'm an old Fortran programmer.
Me too.
But yeah, so they might get into that, but there's an awful lot of C and Python in it too, I think.
Yeah, that would be good. So we're gonna have, so I'm writing down here that Kuldeep is going to revise MSQP science objectives to be consistent with Rob NN4NT's communications. Kuldeep will iterate with the team. Gary is going to work with amateurs to define research questions / procedures for using the MSQP to help us understand what type of performance can be expected from different levels of amateur radio stations. Low cost, modest versus high cost. And I think this is nice too, because if we can tell people, we know that you can do this with a modest station, and this is also a research question, then that might help avoid problems where people are like, oh, this isn't for me because I don't have that type of equipment. It's like, no, you can actually help just get on the air. Even if you are running 5 watts, you could potentially help answer this question. And then Gary can also find volunteers who can modify WSJTX to automatically determine the length of MFSK 144 pings. Possibly include in and one thing I've already done too is Rob Robinette has started to incorporate MSK 144 decoding into the Whisper Demon K9Q suite as well. So we'll be able to use that suite, and then we can also talk to him about setting up channels to save the IQ data to the University of Alabama server. So we actually get the spectrum data as well. I don't think that all of this is going to be accomplished by August. I also don't think that all this is going to be accomplished by December, but I do think that, we, with the grant that Kuldeep and I have, we have like 3 years of funding on this NASA grant, knock on wood. I think that, some of these things, doing this, 2 or 3 years in a row, I think we can really learn some neat things. Rob, do you have a recording of you giving these slides or this talk anywhere on YouTube?
Yeah, I did essentially this talk for you remember the QSO Today Ham Expo?
Yes.
I've forgotten his name now.
Eric Guth.
Eric, yeah.
Yes.
Yeah, I did it. I think it was the first one. But in fact, in that email, I may have provided a link to that. It's still out there on Vimeo, and he was building another kind of repository of all of those talks from the various expos, and it may be on that as well. I think it was YouTube, but last time I looked, it was still on Vimeo, and so it's that talk essentially.
Okay, yeah, I think I found it right.
Yeah, I watched that talk, so it is available.
Okay, good.
Yes.
Would you be okay if we linked to it from the Hamsci page?
Of course, yeah, that'd be great. Yeah,
that'd be great. Yeah, so I think that might be really nice to have up on the Hamsci page, so that if people are wondering what goes on behind all this, I think this will help a lot. And I just found the link. I can put that in the chat if you need me to. It looks like Kuldeep already beat me to it. Good job, Kuldeep. Yeah.
I had a question or doubt.
Yes.
So here we saw things happen in seconds, and the logs which we have are at 1 or 2 minutes. The broader changes over, say, hours, can they be picked in the log files, and the faster changes will be in the 144, this mode which we are seeing, or the logs will be effectively of minimal use or no use? So what are your thoughts? Because they have 1 minute cadence or 2 minutes, or we analyze them at 5 minute interval. Whereas the things which are happening here are mostly for, say, a trail in few seconds. So will there be good exercise to have both, or we can focus first on the second state or later at 5 minute or 10 minute interval?
I am very concerned that
Yeah.
just relying on the spots from PSK reporter is
Mhm.
not going to do what we needed to do.
Yeah.
I'm also concerned that I don't know for sure. I'm not totally satisfied that the way the wave files are saved by WSJT is adequate for us to be able to go back and keep track of the timing and everything. And I'm also not entirely satisfied that we have a good enough system in place to get these wave files from people and make sure we have it in a way that it's going to be useful to us later. We had the same sorts of problems with the solar eclipse QSO party, but in a lot of ways we just ignored, or I kind of ignored those problems because I knew that between the PSK reporter RBN and WhisperNet, and the eclipse was so big that even if the log data people submitted was not useful, like I knew that you could just go to PSK reporter or WhisperNet and we would have more than enough data to kind of do what we need to do. I'm not convinced that's the case here. I don't think we can just rely on the PSK reporter infrastructure for this particular event.
Yeah, and I think the wave files, for those to be useful, you would have to write some software that goes into the wave file, does the decoding, measures the length. So I think that all that's hard. Do it up front. Get WSJT to do that for you. It's already doing most of that anyway. The decoding, all you need is that duration thing. So yeah. Yeah. Having the waves means you haven't thrown anything away. You've got everything, but now you got to deal with it, so
Yeah.
it's not easy.
So I think there are two problems here. One is how to actually process the wave files. But then the other problem is if we have all these volunteers getting on for MSQP, how do we make sure that they have a way of getting us the wave files and or the decoded data from them? And how do we make sure that when they send it to us, they send us wave files that are properly tagged with the receive location, with the time, the date and the time, frequency, all that other metadata that we need in order to make the wave files useful.
Yeah. Yeah, that's a good point. While you're modifying WSJTX to get the durations, the metadata could be extracted from WSJT, stuff like their grid square. Some people put in their 6-digit grid square, but at least the 4-digit, so you know where they were. I don't remember if the like antenna and power level is in WSJT, but that's something else to think about. Yeah, getting that tagged with whatever data they're sending you. Yeah.
I think we're at an hour and a half now, so we should probably break for today. But I think I think it'd be best for us to continue this discussion at some point in the near future. What do you think?
I'd love it. Yeah.
Yeah.
This is fun.
So, I guess the question is when to do that.
If you were looking for kind of a weekly cadence or biweekly, this is a really good date and time for me. I'm working half time, and this is one of my days off. So this is super. I can make other times work, but Thursdays I can't make work, and usually Mondays I can't. But today's great. Today or Friday.
And my Thursdays, I looked at all my Thursdays for the summer, and they are. I've got something going on every Thursday.
Yeah.
Should we plan on, at least for the summer meeting at this time?
Sure.
Works for
Is
me.
that good? Is that good for you, Gary?
Yeah, that would work
Okay.
most weeks anyhow.
Yeah, there's some weeks I can't do it either.
And we all got vacations and whatnot coming up, so
I know.
those are important too.
And they're yes, there are a lot of things going on. Let's see. How about if we at least say for now should we meet again next week at this time? And
If
kind of
that
take
gives
it
Deep and Rob enough time to collaborate between now and then.
okay. That sounds great.
You
So
said you
10
had two students working on this project. Is that is that obviously in the future or?
It's supposed to be now. So, well, one of them told me that he was going to be on vacation this week. So he, there's a reason that he's not here because he told me ahead of time. The other student, I'm not sure what's going on with this person because, this person has missed a number of meetings this week. So I don't know they did send me an email saying they had food poisoning on Monday, but that was Monday. So I don't know what's happening now. So I don't know. But yes, we're supposed to be getting some students as well.
So who's the one that couldn't come today? Is that Declan?
Yeah, Declan told me he had vacation, yes.
Okay, I'll put it on an invitation for a week from today at the same time then. Does that sound good?
That sounds great.
Okay. In the meantime, I've got to run. My wife and I are going out of town, so.
Oh, have fun.
All right.
Yep.
Thanks,
Hang it-
Gary.
Zip and lining through the trees, so.
Whoop, whoop, whoop.
I'm
Different kind of,
I'm gonna go for a bike ride now.
well, that's actually this afternoon. Zip lining's tomorrow, so.
Okay.
All right.
Thanks, Gary.
Thanks, everyone. Take care.
All right.
Thank you,
Bye-bye.
Rob.
Talking with you.
Bye,
Thank you.
everybody.
Bye-bye.